What is the difference between NLP and LLM? Both terms belong to the field of AI, but they describe different things. Let us explain the difference in 5 layers, from the simplest answer to an NLP crash course. NLP stands for Natural Language Processing. It's a broad field of computer science focused on teaching machines to understand human language. NLP can refer to everything from spell check to Google Translate to the bot that detects spam in your inbox. LLM stands for Large Language Model. This is a type of NLP. ChatGPT, Claude, Gemini, these are all LLMs. They predict what word should come next so they can hold a fluent conversation. AI is the field of computer science, NLP is a subfield of AI, and LLMs are a specific technology within NLP. If this answers your question, we were happy to help. But if you're still curious, let's dive a layer deeper. LLMs are the most advanced approach to NLP, but it doesn't mean everything that came before is now irrelevant. Other types of NLP that are still widely popular. Social media platforms use text classification to moderate content. These are very small machine learning models that learn to sort things into categories, like needs moderation, doesn't need moderation, based on the patterns they found in the training data. Early versions of sentiment analysis technology were basically a scorecard. Positive words like love or great add points, negative words like terrible or broken subtract points. Tally it up and you get a sentiment score. Modern versions are smarter, but the core idea is scoring language. Older search engines match your keywords against documents using techniques like TF-IDF. If you search the best AI consulting company, the engine finds documents where those words appear most frequently and most uniquely. A word like the appears everywhere, so it's worth nothing. Words like AI and consulting are more specific, so they score higher. It's math on word frequency. There are many other technologies under the umbrella of NLP, but except for very specific use cases, they proved to be stepping stones towards LLMs. They competed with LLMs to solve the general problem of making machines understand and generate human language and lost. The core trade-off is capability versus cost and reliability. Simpler NLP tools do one thing, but they are cheap, quick, and predictable. A spam filter runs on minimal compute power, never hallucinates, and makes the same decision every time. An LLM can do everything, but it's expensive to run, slow, and unpredictable. Ask it the same question twice, and you might get 2 different answers. It can also be confidently wrong, which a rule-based system simply cannot be. If this still doesn't answer your question, let's look into the history of the NLP field. With the spread of LLMs, the term NLP received a second colloquial meaning. It's used to describe the generation of NLP technology that came before attention and transformer technologies. Remember when machine-translated menus looked like this? Why did this happen? Chinese characters carry many meanings depending on context and the characters appended to them. Rule-based translation tools could only pick the most common meaning of each character. This problem is not unique to Chinese. Even if the translators could record phrases like riverbank to convey a meaning different from the 2 words individually, in sentences like, after walking along the river, she sat at the bank, the model could not see that the 2 words are connected. Recurrent neural networks were the first serious attempt to use neural networks on language. The key idea was to process words one at a time in sequence, carrying a short memory of what came before. Long short-term memory networks fixed RNN's biggest flaw. They forgot things too quickly. An LSTM could hold on to information from much earlier in a sentence, making it far better at tasks like translation or summarization. But their memory still faded over long distances. The real breakthrough for this specific problem was the attention mechanism, which was developed alongside RNNs and LSTMs. Attention let the model look back at any word in the sentence at any point, regardless of distance. So when translating bank, it could directly check that there's river, signaling that the text is not talking about a financial institution. RNNs and LSTMs were a breakthrough, but they had a hard ceiling. Because they processed language sequentially, training them on massive data sets was slow and expensive. LLMs are built on transformers, which process the entire sentence at once and calculates how every word relates to every other word. That unlocked a completely different scale. Instead of training on millions of sentences, they could train on the entire internet. Gen 1 and Gen 2 NLP tools were built for specific jobs. LLMs were trained on so much data that instead of learning one task, they learned language itself. LLMs use computation resources more efficiently than LSTMs, but you, most likely, still cannot afford to build your own LLM. There are 2 separate phases to how LLMs work. training, and inference. Training is when the model runs massive volumes of data through itself and through a process of trial and error, adjusts the strength of connections between neurons, called weights, until it gets reliably good at predicting the training data. This process requires clusters of thousands of high-end GPUs or TPUs running for weeks, plus the capital cost of that hardware and the electricity to run it. Sourcing, cleaning, and licensing high-quality data at this scale is its own expensive pipeline. Then, RLHF and safety evaluation add rounds of human labeling and additional compute on top of pre-training. OpenAI, Google, Anthropic have absorbed the training cost and now offer access to their models. What we do is called inference with the models these companies provide. That takes a fraction of a second and less than a cent. Traditional machine learning used shallow models with 1 or 2 layers that required humans to hand engineer the features. Deep learning is distinguished from simpler ML models by the number of layers. The early layers of an LLM learn simple things like spelling patterns, which letters tend to follow each other, and basic grammar. The middle layers start learning word relationships, that uncle and aunt are related the same way man and woman are, that Paris and France go together the way Berlin and Germany do. They do it by placing every word somewhere in a multidimensional space. In this space, there is a gender direction and a capital direction. The deeper layers learn higher-level concepts. They operate abstract ideas rather than individual words. More layers, more parameters, more training data give the model more room to develop richer internal representations. This is why more scale allows models to come so close to human reasoning. An LLM doesn't return a label, a score, or a translation. Its output is the probability distributions over words. Then it picks the next word, not always the most likely one, and runs again. Every generation is a model guessing what's likely to come next to perform its task of being a helpful AI assistant. LLMs have no way to distinguish between what they know and what sounds right. When they don't have enough signal in their training data to answer confidently, they don't say, "I don't know." This can be mitigated to some extent, but the underlying architecture carries this flaw. A model trained exclusively on millions of product reviews to detect sentiment will always outperform an LLM on that exact task. It's smaller, faster, cheaper to run, and it's never distracted by everything else it knows. But more importantly, it's explainable. Even if a system is not strictly rule-based and employs neural networks, there is a range of explainability tools that can lift the hood to an extent and show how a model made a decision. AI scientists can see which neurons light up when a model is doing a specific task, but not what these neurons represent. In a model with 1 to 2 layers, you can experimentally find neurons that activate when it sees the word free, followed by an exclamation mark, which is why this email got flagged as spam. That's useful, auditable, and legally important in industries like finance, healthcare, or HR. In an LLM, meaning is distributed across thousands of neurons simultaneously, with no single neuron responsible for a single concept. So the concept of spam isn't stored anywhere specific. It's an emergent pattern spread across an enormous web of interactions between neurons. This is called the black box problem, and it's one of the most serious open challenges in AI. An LLM can give you a wrong or biased answer, and there's currently no reliable way to trace exactly why. Because companies cannot train their own LLMs, the data has to be sent to an external server with every query. For most industries, that's fine. For finance, healthcare, legal, or defense, that's a serious security and legal problem. Enterprises have 3 realistic options: pay for external API access and accept the data risk, fine-tune a smaller open-source model on their own infrastructure, or build internal guardrails that prevent sensitive data from ever reaching an external model. So to summarize, Layer 1, NLP is a field of AI science. LLMs are a technology within the field of NLP. Text classification, sentiment analysis, and search engines are NLP tools specialized in a narrow task that survived the invention of LLMs. RNNs and LSTMs allowed models to read a whole sentence before committing to a meaning, thus giving the models memory and basic context understanding. But reading the text sequentially is computationally expensive, and meaning still fades over time. LLMs solved this by processing every word simultaneously, learning how every word relates to every other word at once. This gave models the scale needed to train on all of human language and learn to operate high-level concepts. Despite their power, LLMs come with fundamental trade-offs. They hallucinate because they predict, rather than retrieve. They're black boxes that can't be audited, and they pose a security concern when working with sensitive data, which is why narrow NLP tools, for the right use case, are still the smarter choice.